Hello friends. Today let's try to continue and complete the module on external flows. We have discussed several things about external flows in the last couple of classes. We started with the concept of boundary layer. Before that, we of course derived the governing equations starting from the Reynolds transport theorem applied to a differential control volume, and derived the differential equations for transport, conservation of mass, conservation of momentum, conservation of energy, and conservation of mass of species. In external flows, we basically looked at the flow over a flat plate, which is simplest of the cases of external flows. I talked to you about external flows and their examples. So, flow when it's happening over bodies, the solid is inside and the fluid domain is surrounding it, it's called an external flow. And the simplest of those is a flat plate over which a flow is going. So, there is a thin layer of the flow adjacent to the body called the boundary layer, which is where all the gradients are, and far away from it there is uniform flow. So this I had given you an example of the flow over airfoils, the flow over automobiles. So these are external flows, and it is what is happening in that thin boundary layer that causes the interaction between the solid and the fluid. And the interaction between the solid and the fluid in terms of mass transfer, heat transfer, and momentum transfer is what we are looking at. The momentum transfer between the fluid and the solid results in the frictional drag that happens on the surface, and the frictional drag results in the plate being dragged along with the fluid, or when the fluid is stationary and the plate, which is basically the surface of the object that is moving, a bus or an automobile or an aircraft which is moving in stationary air, the momentum interaction between the stationary atmosphere and the moving object drags the object towards rest and therefore opposes the movement. Okay, and this is one of the reasons why we need to spend fuel, and the higher the drag, higher the fuel being spent, and therefore in aerospace there is a lot of effort and money being spent on controlling the boundary layer drag. Okay, so this is what we call as the frictional drag, and when the frictional shear stress, that is a frictional drag force or frictional force per unit area, is not dimensionalized with respect to rho u infinity squared or rho infinity squared by 2, you get the skin friction coefficient Cf. And the skin friction coefficient can be defined in terms of the velocity gradient at the wall, and using that we had said that the velocity gradient at the wall is going to depend on the square root of the Reynolds number. Okay. So this is the expression that we wrote. The skin friction coefficient goes as 1 over square root of Re, and therefore the shear stress itself goes as the Reynolds number. So the drag actually has reducing trend with respect to Reynolds number. As the Reynolds number increases, it goes as 1 over square root of Re, and therefore the Cf comes down. So the shear stress, which is Cf times rho u infinity squared by 2, or Cf by 2 times rho u infinity square, that decreases as the Reynolds number increases. This is what you see. Okay, and the quantities such as heat and mass transfer, we found that according to the governing equations have very similar equations to momentum transfer, and therefore when we can normalize the equations in such a way that at the surface the dependent variable is 0 and at the free stream it is 1, then the heat transfer equation, which is the energy equation, the mass transfer equation, which is the species conservation equation, and the momentum transfer equation, which is the momentum equation, all of them have similar forms, particularly for the flat plate boundary layer, because the dp by dx is 0. So you get solutions which are analogous to each other. And we looked at the way of calculating one from the other using the Reynolds analogy when Prandtl number and Schmidt number are equal to 1. That is, Prandtl number is the ratio of nu and alpha. Nu is the momentum diffusivity, which is the kinematic viscosity, and alpha is the thermal diffusivity, which is the diffusivity of heat. Now, nu by alpha, when it is 1, nu and alpha are equal, and therefore the delta, that boundary layer thickness over which the velocity goes from u is 0 equal to u equal to 0 to u equal to u infinity, and the thermal boundary layer over which the temperature goes from T is equal to Ts to T is equal to T infinity. The thicknesses of these two become same when Prandtl number is 1, and therefore the shear stress Cf by 2 that you get becomes equal to, or Cf by 2 into Reynolds number becomes equal to the Nusselt number, right? Or Cf by 2 is equal to Nu by Re. This is what you get. In the same way, the analogy for mass transfer gives you Cf by 2 is equal to Sherwood number divided by Reynolds number. Okay, so you get the non-dimensional gradients of the velocity, theta, temperature, and Ci tilde, the concentration, become equal, because of which solution which you derived for one can be used for the other things as well. And by doing an order of magnitude analysis on the equations, we were able to arrive at the forms of these solutions. That is, if I write the Nusselt number as a function of Reynolds number and Prandtl number, what powers of Reynolds number and Prandtl number would the Nusselt number depend on, where it was possible to derive even without solving the equation by just understanding the boundary layer approximation, where the boundary layer is thin, okay, as compared to the object's dimensions, and accordingly you get the orders of magnitude of the various terms. And by putting them together, we were able to see that the Nusselt number always depended on Re to the power of half, irrespective of whether the Prandtl number is 1, less than 1, or greater than 1. But the power of the Prandtl number varied. In the case of Prandtl number much less than 1, we get Prandtl to the power of half, and in the case of power of in the case of large Prandtl number, the power of Prandtl number is 1 by 3. Right? So this is what we looked at. So we got Nu is equal to some constant times Re to the power of m Pr to the power of n. The m is always half, and the n is half in the case of low Prandtl number, and 1 by 3 in the case of large Prandtl number. And we were able to get the results from experimental data or from analytical solutions to match very well with these powers, and the constants were also determined. Okay. So this is something which we said is the result for laminar flow over a flat plate. So in today's class, we will extend the Reynolds analogy to be able to use analogy of momentum, heat, and mass transfer also for cases when the Prandtl number is not equal to 1. So we go through what is called the Colburn or the Colburn-Shelton analogy for Prandtl numbers larger than 1. Okay. That is something that we will look at today. And in today's lecture, we will also look at what happens in turbulent flow. So in laminar flow, the power of Reynolds number was always half. In turbulent flow, the power of Reynolds number changes. Okay, and this is something that we will just write and give the correlations, so that we can write the expressions for Nusselt number and shear stress when the flow is laminar, and write for when it is turbulent. We'll also find out when the transition happens, and in the case of a transition over a flat plate, how do we calculate the average Nusselt number or the average heat transfer coefficient. Yesterday we talked about integrating the heat transfer coefficient over the surface for getting the average Nusselt number, the average heat transfer coefficient, and from there average Nusselt number by integrating the local heat transfer coefficient over the surface. Now, if the local heat transfer coefficient is partly laminar in one part of the plate and partly turbulent in another part of the plate, how does this integration change is something that we will look at today. Okay, and with that, we will also look at a few finer points regarding the calculations of heat transfer coefficients for external flows and close the chapter on external flows today. Okay, so that is basically what we will do. So let's now move on to the whiteboard to start the discussions on the analogies, particularly when the Prandtl number is not equal to 1. Okay, so we saw that in Reynolds analogy, when Prandtl number is equal to 1 and Schmidt number is equal to 1, or maybe of the order of 1 if I say, okay, we use the Reynolds analogy. In which we said Cf by 2 is equal to nu x by Rex. This is Cf x by 2, and that is equal to Shx by Rex. This is basically what we wrote. Okay. Now, this is when the Prandtl number and Schmidt number are 1. In the case of non-unit Prandtl number, we found that the correlation for Nusselt number at larger Prandtl numbers matched fairly well with the Reynolds analogy expression. So we said for Prandtl number greater than about 0.5, you got the Nusselt number at any x as equal to 0.332 Rex to the power of half Prandtl to the power of 1 by 3. Okay. Now, you remember that this expression is something that we are already familiar with. That is, when Prandtl number equal to 1, that was the Nusselt number. So, in this case, this was 0.332 into Rex to the power of half Pr to the power of, it's okay, the Prandtl number we don't write here, Rex to the power of half. The Prandtl number is 1, this remains as 1, okay, and this divided by Rex, that will be that was the Cfx by 2, and the Cfx by 2 is still the same because the fluid flow is the same. Whether it's Prandtl number higher than 1 or lower than 1, fluid flow remains the same because the Prandtl number does not affect the fluid flow solution, and therefore you get 0.332 divided by Rex to the power of minus half for Cf by 2. This is the expression that you get. So when Prandtl number is non-unity, then there is an additional term Pr to the power of 1 by 3. So what is done is to define a J factor Jh for heat transfer and Jm for mass transfer, which is defined as nux divided by Rex Pr multiplied by Prandtl to the power of 2 by 3. Okay, so this is a quantity that we define. So what is this then? Basically, Pr to the power of 2 by 3 by Pr is Pr to the power of minus 1 by 3. So you are basically dividing the Nusselt number by Reynolds number and Prandtl number to the power of 1 by 3. So basically, this quantity is often referred to as Stanton number, STX. And so what you write actually is, this is Stanton number multiplied by Pr to the power of 2 by 3. Okay, and Jm is likewise defined as Shx, which is the Sherwood number at any x, divided by Rex Pr multiplied by, not Pr, is Schmidt number, sorry. In mass transfer, you just replace the Prandtl number with Schmidt number multiplied by Schmidt number to the power of 2 by 3. which is nothing but, you call this as STM, which is the Stanton number for mass transfer at any x multiplied by SC to the power of 2 by 3. Okay, so this is Jm and Jx, and according to the new analogy or the Colburn-Shelton analogy, we say that Cf by 2 is actually equal to Jh, which is equal to Jm, which is given by this. Okay, so the Colburn-Shelton analogy simply tells you that the Cf by 2, which is the non-dimensional shear stress coefficient, or nothing but the skin friction coefficient, is not equal to Nu by Re or Sherwood by Re, but instead equal to Nu by RePr into Pr to the power of 2 by 3, or Sh by ReSc into Sc to the power of 2 by 3. So this gets replaced by this term, which is Stanton number multiplied by Pr to the power of 2 by 3. So we write the Colburn-Shelton analogy, which basically is valid for Prandtl numbers greater than about 0.6. Okay, it basically says Cf by 2 is equal to St into Pr to the power of 2 by 3, which is called Jh, the J factor for heat transfer, which is equal to Stm multiplied by Schmidt number to the power of 2 by 3. Okay, so this is basically the analogy that you normally use, and this is called Jm. Okay, so Cf by 2 is equal to Jh equal to Jm is called the Colburn-Shelton analogy. Okay, so the moment I have the fluid flow solution and I know the Reynolds number and Prandtl number, from this expression or this expression I should be able to get the heat transfer coefficient or the mass transfer coefficient. Let us understand how. So once I know the fluid flow solution, I know Cf by 2, then Nu by, this is Nux divided by Rex Pr multiplied by Pr to the power of 2 by 3 is equal to Cf by 2. Okay, so this is a known value and RePr are all known values. So I can write Nux is equal to, this is Cf at any x, so Cfx by 2. Okay, that multiplied by okay, let me write the by 2 below. Cfx by 2 multiplied by, this will be Rex. Okay, and this will be Pr to the power of 1 by 3. So this is basically what you get, and you can verify that at Prandtl number equal to 1, this becomes 1, and this reduces to the Reynolds analogy, it is Cfx multiplied by Rex. And from this Nusselt number is nothing but Hx into x by Kf. So if I know Kf, and I of course know the value of x at which I have determined the Cfx, and therefore I should be able to get Hx, which is the heat transfer coefficient at the same location. So if I know the fluid flow solution and therefore Cfx at any x value, then I should be able to determine the heat transfer coefficient value Hx at the same location, and this is valid irrespective of whether the flow is laminar or turbulent. Okay, so this is something that has been observed, that whether it's laminar flow or turbulent flow, the Colburn-Shelton analogy is still respected, and therefore we can still use the Colburn-Shelton analogy even otherwise. So this is your expression. Similarly, Sherwood number Shx can be written in the same way, Cfx by 2 multiplied by Rex into Schmidt number to the power of 1 by 3. So this is another okay, the Cf by 2 is common to both of these. So this is the way in which, and this Sherwood number is nothing but hm at any x, mass transfer coefficient, multiplied by x by d, where d is the diffusion coefficient for the solid into the fluid. So this is the expression. So once I know the Cf by 2 and the Reynolds number and Schmidt number, I can find out the mass transfer coefficient and the heat transfer coefficient, and therefore the convective heat or mass transfer rates can be established straight away from the solution of the fluid flow. So this is a very powerful result, because you saw that the equations that you are solving are complex, and in order to solve them numerically or analytically, it requires a certain amount of mathematical skill and ability, or a computer program to be able to do that. So if I have the solution of one of the equations, and from that I'll be able to write the others using the analogy between momentum, heat and mass transfer, it's a very powerful method. So if I, for example, want to do experiments and I'm able to measure, let us say, only the drag force on a surface, then using the drag force per unit area, which is the shear stress, and dividing it by rho u infinity squared, I get the Cf by 2. And once I get the Cf by 2, I can actually also get the heat transfer coefficient. So if I get the average shear stress, I'll also be able to measure the average heat transfer coefficient. And if I get the local shear stress, I'll be able to measure the local heat transfer coefficient. So this is a very powerful result. Knowing the for fluid flow result, we should be able to get the heat transfer result and the mass transfer result using the analogies. Okay, so this is the part that I wanted to introduce to you first. Not only when Prandtl number or Schmidt number equal to 1 can we use the analogy, because that is something that we had learned in the previous class, that the Reynolds analogy can be used when Prandtl number and Schmidt number are 1. What we find is that the Colburn-Shelton analogy can be used even when Prandtl number is not equal to 1, but it is greater than 0.6. What is interesting is that for Prandtl number less than 1, the results of heat transfer and mass transfer can be directly related to each other. So that is not a problem. But for Prandtl number greater than 1, you need to bring in the Prandtl number. Okay. So this is the interesting result, that we should be able to use the fluid mechanics solution to get the heat transfer coefficient as well as the mass transfer coefficient. Okay. And this is also valid in turbulent flows. We will be talking about turbulent flows shortly in today's lecture. It's also valid for turbulent flows. So this is one result that we will understand. The second thing that we would like to understand today is laminar and turbulent flow. Okay. So let us recall what is called the Reynolds experiment. Osmond Reynolds is a person who lived in the late 19th century, and he was the one who first used the distinction between laminar and turbulent flow. He didn't use the word turbulent. He used to call it direct flows and sinuous flows. This is the distinction that he said. Later the flow came to be known as, this was called the laminar flow and this was called the turbulent flow. That came later, but it was the Reynolds experiment which brought that forward. So anyone who is interested may just Google Reynolds experiment and look up YouTube videos. So you should be able to see what kind of experiments Reynolds actually did. So what he did was, he just took a long glass pipe into which he had water flowing from a tank. Okay, so it was connected to a tank and water was flowing in it, and he had small syringes that were available with him, through which he used to inject a small blob of dye. So let us say the dye is the magenta color. If he injected a dye in this, when the flow rate, he used to measure the flow rate by collecting this is wrong color. So by collecting the water at the end of the pipe, So by collecting the water at the end of the pipe and measuring using our stopwatch how much time it took for a certain amount of water to collect, so he knew the flow rate, which is the number of liters per second that collected in this, and from this dividing by the area, said U multiplied by A is Q dot, which is the flow rate. So dividing by the area, he used to get the average velocity of the flow through the pipe, which is U. Okay. Now he varied the flow rate through the pipe by adjusting the water level in the tank or some such method, and then for a certain flow rate or a certain U, he used to inject a dye. Okay, so now we'll go to the respective gunner. Okay, now he used to inject a dye and observe how the streak of dye goes through the liquid. Okay, and he also had multiple syringes. So he used a syringe, for example, which had let's say so many syringes. Okay, and he used to introduce this and look at it at any given instant of time. So what he found was that the dye that came from the center used to travel the farthest. The ones which were other than that traveled lesser and lesser and lesser. So he was able to get something like a velocity profile which could show that the velocity of the center line was the largest and the rest of the lines had smaller velocity, and these streaks would remain unmixed, and that way it used to just progress. Okay, so this is an interesting result that he used to get. When he increased this velocity, okay, the velocity was increased to higher and higher values until a certain velocity. He observed that these streaks would remain smooth without mixing with each other, but beyond a certain velocity, these streaks used to start oscillating. These used to start oscillating and eventually got mixed in the downstream. Okay. So he experimented it with a whole variety of different fluids, different pipe diameters, and different velocities, and eventually arrived at a combination of density, velocity, diameter, and the fluid viscosity, and said that this is a non-dimensional group, and when this group exceeds a certain value, in the case of a pipe, he found when it exceeds, let us say, about 2000 to 2300, when it exceeds this range of values, then this kind of sinuous behavior started getting exhibited, and when the group, non-dimensional group, which is later called the Reynolds number, okay, this we defined a Reynolds number for our flat plate also. If he found that when the Reynolds number for a circular pipe was less than 2300, then the flow had more stability and therefore it remained laminar. And when the velocities were increased, or the diameter was increased, or the viscosity was decreased, this combination, when it was changed so that its value exceeded 2000 to 2300, then the flow had tendencies of becoming turbulent. So basically he said that there are two regimes of flow, one in which the flow is direct, where it is smooth laminae without mixing with each other, another in which the flow is sinuous, disturbed, and the mixing becomes more, and that is determined by this non-dimensional group. For a circular pipe, values between 0 and 2000 through 2300, the flow remained laminar, and values exceeding 2300, the flow became sinuous or turbulent. So this is the experiment that Reynolds had done, and this was done for a pipe flow. But what we observe that the transition from laminar to turbulent flow happens practically in every configuration or geometry, and the flat plate is no exception. Okay, so if I do a similar experiment on a flat plate, so let us say there is flow going here, and I put multiple multiple syringe injector, then the velocity profiles went higher and higher in speed as you go there, and less speed when it go here. So you have a profile which looks like this, and the velocity is 0 at the surface. So this was something which is possible to observe. That is one thing. So we were able to visualize the edge of the boundary layer. You inject it at different locations, the edge of the boundary layer is different. So the thickness of the boundary layer can be found from there. So this is one thing that could be observed. And the streaks remained laminar, that is without mixing with each other, until a certain combination of rho u infinity, if I u infinity is the faraway velocity, rho u infinity into x by mu, where x is the distance from here. Okay, so what is observed is that when this, for the same value of rho mu, that is the same fluid and the same u infinity, the same velocity, as x increases, there is a certain limit of x up to which the flow remains laminar, beyond which the flow becomes turbulent. And for the external flow, this combination is around 5 into 10 to the power of 5, and if the Reynolds number is less than 5 into 10 to the power of 5, the flow has the tendency to remain laminar, and if it exceeds this value, then the flow has a tendency to become turbulent, which basically means that these laminae would get disturbed and eventually get mixed up in this region. Okay, so when you inject it from here, until this distance the flow remains smooth, and after this distance the flow starts getting mixed up and becoming turbulent. So what is observed in external flows is that if I have a flow like this, the flow remains laminar, the laminar boundary layer edge shows like this for a laminar flow, and after that there is a certain amount of disturbance that happens, and then there is a certain other behavior of the boundary layer. Okay, so this region in this side of the thing, which is less than 5 into 10 to the power of 5. Okay, so if I plot Rex here, when Rex is up to 5 into 10 to the power of 5, the flow remains laminar, and between 5 into 10 to the power of 5 and maybe a slightly higher value than that, maybe 10 to the power of 6, maybe 2 into 10 to the power of 6, there is a region where the flow is neither fully laminar nor fully turbulent, which means in some parts of the boundary layer the flow is laminar and some parts it's turbulent, so it is undergoing a transition. Okay, so this is the laminar region, this is the transitional region, and here the flow is fully turbulent. Okay, so this is something that is observed on a flat plate boundary layer, and the critical Reynolds number for transition is identified to be 5 into 10 to the power of 5 by various experiments. There are people who also work on mathematical stability of these flows, and using the stability theory and perturbation analysis also, the limits of stability of laminar flows has been determined theoretically. That's also available. So this 5 into 10 to the power of 5 is the number for external flows, whereas 2000 to 2300 is for internal flows through a circular pipe, right? So that is the expression that we have. So that is the Reynolds number beyond which the flow would not remain laminar. So if I look at a flat plate boundary layer, then a part of the flat plate boundary layer would remain laminar and the remaining part would be turbulent, and there is a certain region in between which is transitional. It's difficult to quantify what happens in the transitional region because it's intermittent flow, partly laminar, partly turbulent, sometimes laminar, sometimes turbulent, and so on. And therefore what is normally done is to extend this regime and extend this regime and see some place where they meet and take this 5 into 10 to the power of 5 as the limit of the laminar flow in that sense, and you say that the flow remains laminar up to 5 into 10 to the power of 5. After that it becomes fully turbulent, which is an approximation, but it can still be done. So then we'll be able to write the set of expressions that we already derived for heat transfer coefficient in terms of Cf by 2, etc., can be applied to the laminar region, and we require a similar set of expressions for the turbulent region, so that if I want to calculate what happens in the entire plate, then I'll need to integrate over the plate through the laminar region and through the turbulent region to get the overall heat transfer coefficient or the average heat transfer coefficient over the plate. Okay. So first let us write down the expressions for fully turbulent flow boundary layers, and then we will write for boundary layers which have partly laminar and partly turbulent. So in order to do experiments on fully turbulent boundary layers, what people used to do was to have a velocity which is reasonably large, and then they used to have a small what is called a trip wire, okay, which basically is nothing but a small wire which actually trips the flow here. So the flow has to jump over it as the flow comes here, and this disturbance is good enough to make the entire boundary layer turbulent, because the Reynolds number corresponding to the length of the plate would be quite large, and therefore the boundary layer would be turbulent in the entire region, and the whole boundary layer would behave turbulently. The turbulent boundary layer has an interesting characteristic. In the laminar boundary layer, we drew the velocity profile something like this, where there is a smooth variation from laminar to turbulent, which gradually changes from 0 to u infinity. In the turbulent boundary layer, even if this is your u infinity, the boundary layer is very sharp and the flow becomes like this. So even if the edge of the boundary layer is somewhere here, there is a closed region of the boundary layer near the wall where the gradient is very sharp, and after that the gradient is gradual. This is something that has been found by experimental measurements. So this is a laminar boundary layer profile, and this is a turbulent boundary layer profile for u versus y, okay, where y is the distance above this and u is the flow velocity. And the other thing that you need to know is that this u is actually not so smooth, because we said that in turbulent flow there is a lot of mixing, there is a lot of disturbance, and therefore the flow at every location has eddies that are rotating in both directions. So if I measure velocity at one location as a function of time, so if I put u as a function of time, even when there is steady state happening everything is steady, you will find that there will be a mean velocity about which this u would actually be fluctuating. Okay, so this mean is called, let's say, u bar, which is obtained by taking a certain time interval t1, which is sufficiently large as compared to the small oscillations that you typically see, and do an integral of u dt, okay, and 1 over t1. This is something that you do. Okay, so you determine the area under this curve from this location to this location and divided by this t1, so you get this average. So what you plot here actually is the mean velocity in turbulent flow and not the instantaneous velocity. So at any location, therefore, u would actually be u bar plus a u prime, which is the fluctuation at that instant, and this is continuously changing, and you can actually take it to be a statistically random quantity, and the magnitude of this u prime would depend on the extent of turbulence that is present, and if the flow is very turbulent, that is when the disturbances are oscillating very rapidly, then you call it a very highly intense turbulence. The u prime would have a large magnitude, otherwise the u prime would have a small magnitude depending on the nature of turbulence. Okay, and this nature of turbulence depends on the extent of tripping that happens or the extent of disturbances that exist in the free stream flow. That determines how turbulent a given flow is, and the more turbulent a flow is, the more vigorous are the eddying actions that is there. So you will have small eddies, you will have the large eddies that come from the main flow, and near the wall, because of breakup of those eddies, they become smaller eddies in this region. So if I introduce, for example, a die from here, the die naturally cannot remain smooth, but it will get carried by this a little bit, and then this a little bit, and this a little bit, and this a little bit, and therefore it actually diffuses very, very quickly and disappears in a very, very short distance. And that is the nature of turbulent flow that you normally have. Okay. So this is what we understand by turbulent flow. Turbulent flow is something which is very highly eddy dominated, and therefore large sized eddies break up into small sized eddies, and finally near the wall, because of viscosity, those eddies are completely controlled, and so very close to the wall the flow remains nearly laminar, but that is extremely small fraction of the turbulent boundary layer, and the remaining part of the turbulent boundary layer, there is a lot of fluctuations that happens because of the eddying action. Okay, and the different sizes and scales of eddies determine the extent of oscillations and the extent of mixing that would happen because of the turbulence. Okay, so this is what turbulence is. We will not go further too much into turbulent flows, but what we will do is, when the flow is turbulent, then how does the Nusselt number depend on the Reynolds number and Prandtl number is something that we will write, and we will close the discussion on turbulent flows with that. So what we have found from experimental data is that delta by x, we have to be in black, delta delta by x is of the order of Rex raised to the power of 1 by 5 in turbulent flows. Okay, this is in comparison with Rex to the power of minus 1 by 5. This is in comparison with Rex to the power of minus half in laminar flows. Okay, so as the Reynolds number goes higher, the boundary layer becomes thinner. So the delta by x goes as Re to the power of minus 1 by 5 in case of turbulent flows as compared to laminar flows. And the expression for the boundary layer thickness would be 0.037 into Rex to the power of minus 1 by 5, which is obtained by experimental measurements for turbulent flows. Also computations confirm this. Okay. Then CFX, because CFX is going to depend on 1 over delta, because del u by del y is of the order of 1 by delta by x, and therefore it will be of the order of this. So CFX is equal to 0.0592 into Rex to the power of minus 1 by 5 in turbulent flows. In comparison with that, this is up to 10 to the power of 7 and up to sometimes 10 to the power of 8. So this is valid when Rex is less than 10 to the power of 7, and up to Rex less than 10 to the power of 8, this is valid with about 15% error. Okay, so up to here you can use it with reasonable accuracy, but up to 10 to the power of 8 you can use it assuming that there will be up to 15% deviation from the value. Okay, and using the Colburn-Shelton analogy, now we can write the expression for Nusselt number. So the Nusselt number NUX, this will be CFX by 2 into Rex PR to the power of 1 by 3, right? So this is basically what we wrote in the Colburn-Shelton analogy. Okay, so since there is a RE to the power of minus 1 by 5 here, and this there is a divided by 2, you will get 0.0296. This is 0.0592 divided by 2 into REx to the power of 4 by 5 and Prandtl to the power of 1 by 3. Okay, so this is your Nusselt number, local Nusselt number, and this is valid for 0.6 less than Prandtl number less than 60. Okay, so for practically all fluids whose Prandtl numbers are between 0.6 and 60, the Nusselt number can be written in terms of this, and this is directly obtained from the Colburn-Shelton analogy. Using this expression, you have written this. Okay, so by the Colburn-Shelton analogy, the Nusselt number for turbulent boundary layers is 0.0296 Rex to the power of minus 4 by 5 Pr to the power of 1 by 3. Okay, so this is the expression that we need for calculating heat transfer coefficients in turbulent boundary layers. But turbulent boundary layers, we understand that this turbulent boundary layer is something which starts at the leading edge of the plate. That is, when the plate is tripped right in the beginning. Yeah, so we talked about a trip wire right at the beginning here. Okay, so when the plate is tripped right here in the beginning of the thing, so then the x is measured from this location itself, and Rex is defined on the basis of rho u infinity x by nu, where x is the distance from the leading edge. Okay, so this is for a boundary layer which is turbulent right from the beginning. Okay, but real boundary layers actually undergo transition somewhere in the middle, and therefore this expression would be valid only after a certain distance from the beginning. But in the beginning, you would have the laminar boundary layer. So what do we do when a boundary layer is partially laminar and partially turbulent? In order to calculate the average heat transfer coefficient over the plate, we'll need to integrate it over the entire flat plate with both the expressions. So suppose this and this are the things. So this is laminar and this is turbulent, and therefore in this one you will have Hx is, let us say, 0.332 Rex to the power of minus half as Rex to the power of okay, so this is let's first write the Nusselt number, then we'll write the thing. So this is NUX is 0.332 Re to the power of half PR to the power of 1 by 3. Okay, and in this region you have NUX is 0.0296 Rex to the power of 4 by 5 Prandtl to the power of 1 by 3. Okay, now if I want to integrate over this plate to get the average heat transfer coefficient, then in this region Hx is Kf by x multiplied by NUX for the laminar, and here also it is the same. So you will basically get x to the power of minus half here and x to the power of minus 1 by 5 here in the x value, and the remainder has to be integrated in the same way. So h bar would be integral from 0 to xc of h laminar. Okay, so this I'll call it as h laminar, and here I'll call it as h turbulent dx plus integral from xc to L, where L is the length of the plate, of h turb dx. Okay, so this is the expression that you would use, and h laminar can be written from this expression, so that would be equal to 0.332 kf, okay, multiplied by PR to the power of 1 by 3 and rho u infinity by mu whole thing to the power of half. All of this will remain the same. So this multiplied by x to the power of minus half. Okay, so if I make space for this here, then this integral will actually look like integral from 0 to xc of this dx plus integral from xc to L of the remaining part, which will be 0.0296 into kf, okay, and that multiplied by rho u infinity by mu, the whole thing to the power of 4 by 5, which is the part of the Reynolds number, and Prandtl to the power of 1 by 3. All of these are constants, and then you have an x to the power of 4 by 5 divided by x, which will be x to the power of minus 1 by 5 dx. Okay, so this is basically what you will do for integration. Okay, and when I do this integration, I will get the value of h bar, and then the nu bar for the entire plate is defined as h bar into L divided by kf, and this will be your average Nusselt number for the whole plate. So this will depend on where this transition is occurring, and if I do this integration and simplify it, what I would normally end up getting is an expression which looks like this. You will get an nu L bar is equal to 0.664, that the 0.332 gets multiplied by 2 because there is an x to the power of half in x to the power of minus half in that integration, into REXC to the power of half, where XC is the critical distance at which the transition happens, and REXC normally is used as 5 into 10 to the power of 5. Okay, this plus 0.037, so this is basically, you have a minus 1 by 5, so minus 1 by 5 plus 1 by minus 1 by 5 plus 1, we will get a plus 0.8. So you have the 0.0296 divided by 0.8, which gives you 0.037, multiplied by REL to the power of 4 by 5 minus REXC to the power of 4 by 5, whole thing multiplied by Prandtl raised to the power of 1 by 3 is the expression that you will get. Now this REXC is 5 into 10 to the power of 5, so if I substitute the value and simplify this, then I will get this as 0.037 REL to the power of 4 by 5 minus 871, whole thing multiplied by Prandtl number to the power of 1 by 3. This is your average Nusselt number for the entire plate when I integrate the local Nusselt number expression and use this value REXC as 5 into 10 to the power of 5. So 5 into 10 to the power of 5 multiplied by 0.664 minus 0.037 is 871. That's the number that you get. The remainder you get this one. Okay, and similarly, the Sherwood number, averaged over the length, will also give you a similar expression, 0.037 REL raised to the power of 4 by 5 minus 871 multiplied by Schmidt number raised to the power of 1 by 3. Okay. Now this is valid for 0.6 less than Prandtl less than 60, and this is valid for 0.6 less than Schmidt number less than 3000. We found that actually experimentally it's found that it's valid for much larger Schmidt numbers. In both cases, the Reynolds number range validity is 5 into 10 to the power of 5 less than RE less than 10 to the power of 8. This is the range over which these expressions can be directly used. So it's a simple application of Colburn-Shelton analogy to the expression that you had. that is the CF expression that you get. The CFL itself, CF bar L comes out to be 0.074. You can see that that is twice this number divided by REL to the power of 4 by 5, REL to the power of 1 by 5 rather, sorry. Minus 1742 divided by REL. Okay, so this is again valid for this range of Reynolds numbers. Okay, so this is the expression that you get, and in cases where the plate is so large that your laminar part is a very small part of it, say for example I have a very large plate and this much is laminar and the rest of it is turbulent, I can neglect this part of it. So when the Reynolds number is much larger, so this, for example, if I use 10 to the power of 8, find 10 to the power of 5 is a minuscule fraction of it. So in such a case, I can actually drop this because this will be very small as compared to this. So if I do that, then I get a much simpler expression. The NUL will be just this into Prandtl to the power of 1 by 3. This term can be dropped. And similarly, SHL will be just this multiplied by Schmidt to the power of 1 by 3. This can be dropped. This is when the L is much larger than XC, or the Reynolds number is much larger than 5 into 10 to the power of 5. Then I can use dropping of this expression, and similarly I can drop this part of the expression. Okay, so that is the thing that you get for very large Reynolds numbers. But in general, when you have both fractions of pipes which are significant, both fractions of the plate which are significant, the first fraction of the plate which is laminar, second fraction which is turbulent, and let us say a sizable fraction is laminar flow, then this complete expression should be used. So that is about calculating the average Nusselt number or average heat transfer coefficient over the entire plate. One small note about the temperature at which the properties have to be taken for calculating the Nusselt number or Prandtl number or Reynolds number, because the viscosity and sometimes even the thermal diffusivity can be reasonably sensitive to the temperature. For example, water from room temperature to close to boiling point, its viscosity changes by almost an order of magnitude. It's quite a large variation. So it's good to specify the temperature at which you calculate these properties rather than just leave it to choice. So what we call as film temperature is recommended for the calculation of the properties. That is, if I have Ts as the surface temperature and T infinity as the free stream temperature, the mean of these two temperatures, which is Tf film temperature, is called Ts plus T infinity by 2. It is at this temperature that you evaluate all the properties. So you calculate Reynolds number, which is rho u infinity x by mu. You calculate the mu, the rho, both at the film temperature. Similarly, Prandtl number is mu by alpha, which is also written as mu Cp by K. You evaluate all of these properties at the film temperature. Similarly, Schmidt number is mu by D, which is mu by rho D. This again, mu, D and rho are evaluated at the film temperature. So when you do that, and so this K is Kf, of course. So when you do that, then the calculations become more consistent, particularly when between Ts and T infinity the properties have a substantial variation of a particular substance. Okay, so that is one thing that we need to remember. So whenever you calculate the properties for calculating the heat transfer coefficient or skin friction coefficient, it should be calculated at the film temperature, which is the average of the surface temperature and the fluid temperature. Okay, so that is the point that we'll need to note. Okay. So let's take a quick stock of what we did today. So today we first understood the Colburn analogy, in which we say that even for Prandtl number greater than 1, or rather greater than 0.6, we have a method of analogy where we actually write the j factors jh and jm, which is nothing but the Stanton number into Prandtl to the power of 2 by 3 instead of the nu by re or sh by re itself. So Cf by 2 is equal to the jh or the jm in the case of the Colburn-Shelton analogy, and this then makes it possible to generalize the fluid flow results to get the heat transfer and mass transfer results even at Prandtl numbers deviating from 1. So that is the first thing we saw. Then the second thing we saw is what we understand by laminar flow and turbulent flow, and we understood the characteristics of turbulent flow, and then wrote expressions for the heat transfer coefficients and skin friction coefficients typically observed for turbulent boundary layers, and we then calculated the average heat transfer coefficient, average Nusselt number, average Sherwood number, and average skin friction coefficient over a plate by integrating the local heat transfer coefficients. And when the transition from laminar to turbulent is taken to happen at 5 into 10 to the power of 5, we got a certain expression. And we said that when the Reynolds number is much exceeding that number, then this term corresponding to the 5 into 10 to the power of 5 could be dropped, because that would be a very small number as compared to the remainder. So that is something we did, and then we closed with saying that the properties that we need to calculate for obtaining the Reynolds number, Prandtl number, etc. for the calculation of skin friction or heat transfer coefficient should be calculated at the film temperature, which is the average of the surface temperature and the fluid temperature. Okay, so we'll stop here at this point, and with this we come to the end of external flows. Let us try to understand whatever we have done about external flows so far, and then in tomorrow's lecture, what I will be uploading, I'll be talking about internal flows, in which we will be using part of the understanding of the external flows in order to define the concepts that are specific to internal flows. Okay, so we'll stop at this point and continue in the next lecture.